Hey everyone, let's jump right into this explainer on gravitational fields. We're going way beyond the simple idea of what goes up must come down and completely transforming how you think about gravity.
So gravity isn't just some basic downward pull, right? It's literally an invisible field of force permeating the very fabric of space. In physics, we strictly define this as force per unit mass. And by kind of imagining mass acting as a single point right at its center, we can actually map out these field lines to show exactly how space is warped to pull objects in. It's like a cosmic web.
To get a handle on all this, here is our roadmap for the explainer. We'll start by defining the gravitational field, move on to Newton's law of gravitation, check out orbits and geostationary satellites, dive into gravitational field strength, and wrap up with potential and potential energy. Let's get to it.
Section 1. Defining the gravitational field.
You know, physicists have this brilliantly clever trick for dealing with incredibly complex objects. Think about the Earth for a second. It's a massive, textured, totally uneven sphere. But if we mathematically treat the entire planet as if it were just a single point mass located exactly at its dead center, the math just clicks into place. It's a game changer. It lets us draw clean, predictable field lines pointing straight to the core.
Moving right along to Section 2, Newton's law of gravitation. Okay, here is the absolute blueprint of gravity. The force, our F here, between two objects depends entirely on their masses multiplied together. Basically, bigger masses equal a much stronger pull. But look below the line in that equation. That force drops off really fast based on the inverse square of the distance between them. So if you double the distance between two planets, the gravitational pull doesn't just cut in half. No way, it drops to a mere quarter.
And see that big G? That's the universal gravitational constant. 6.67 times 10 to the negative 11. To put that into perspective, that's a 0, a decimal point, 10 more zeros, and then a 6. It's an unfathomably tiny number. But it's basically the secret code governing our universe, perfectly explaining why gravity feels incredibly weak until you're dealing with massive, massive things like planets and stars.
All right, Section 3, orbits and geostationary satellites.
By analyzing circular orbits, we can unlock exactly how satellites stay afloat. When a satellite moves sideways incredibly fast, that invisible gravitational pull acts exactly as the centripetal force needed to whip it into a circle. It's kind of crazy when you think about it. It's essentially constantly falling towards Earth, but it's moving so fast horizontally that it continually misses the ground.
Now, if we want a satellite to stay perfectly locked over your city for, say, continuous GPS or weather tracking, it absolutely has to follow 3 strict rules. First, it needs a 24-hour orbital period. Second, it has to move west to east to match the Earth's spin. And third, it must sit squarely above the equator. If it doesn't, it would just drift north and south every single day, which obviously wouldn't be very helpful.
Next up, Section 4, gravitational field strength. Derived straight from Newton's law, this formula calculates specific gravitational field strength, that lowercase g. It's the force per unit mass from a single giant object, our big M, at a distance r. Notice how the second mass just drops right out of the equation? That's because field strength is a fundamental property of the space around a planet, completely regardless of whether you drop a tiny feather or a heavy bowling ball into it.
Here's something to think about. When you jump up in the air, your distance from the center of the Earth technically increases, right? So shouldn't gravity get weaker? Well, because the radius of the Earth is just massively huge, we're talking over 6 million meters, any tiny changes in height near the surface barely make a dent in the r of our equation. So that keeps the field strength practically locked at roughly 9.81 meters per second squared, no matter how high you try to jump in your backyard.
And finally, Section 5, potential and potential energy.
Okay, buckle up, because this is a totally mind-bending concept. We actually start measuring from infinity. Out deep in space, an infinite distance away from any planet, the potential is strictly defined as 0. As gravity pulls you closer to a planet, work is actually done for you, meaning the potential drops into negative numbers. So think of flat space as 0. Simply standing on a planet means you've actually fallen into a deep, negative energy well.
Take a look at the mathematical contrast here. The r squared on the left gives us the strength of a directional force vector pulling an object. But by dropping that square to just a single r on the right and combining it with a negative sign, we completely map out that scalar potential energy well we just talked about. Basically, one is an arrow and the other is a landscape.
So here is how all these puzzle pieces lock together. When you take that gravitational potential landscape and introduce a second mass into the field, boom, you get the total gravitational potential energy. This isn't just theory, it's the actual, measurable, stored energy that's currently locking the Earth and the Moon in their eternal dance.
This synthesizes the whole shebang. Do you see the beautiful, almost magical mathematical symmetry? The concepts relying on distance squared like force and field strength govern the active pull. Meanwhile, the energy concepts drop the square and carry a negative sign, dictating the stored potential. It's absolutely a perfect mathematical mirror.
So how did these invisible, mathematically perfect fields govern the entire structure of the universe around you? As we wrap up this explainer, I want to leave you with this final, crazy thought. The exact same, totally elegant mathematical rules that pull a dropping apple to your kitchen floor are precisely what hold our entire spinning galaxy together. The math scales up flawlessly. Keep that in mind the next time you look up at the night sky. Thanks for learning with me.